வாரும் வதனமென திகழ்பரத கண்டமிதில் தெக்கனமும் அதில் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை துணலும் தரித்தனமும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்ததுமே வாழ்த்ததுமே வாழ்த்ததுமே. வந்தே மாதரம் வந்தே மாதரம் சுஜலாம் சுபலாம் மலயஜ சீதலாம் शस्य श्यामला मातरं वन्दे मातरम् शुभ्रज्योत्स्ना पुलकितयामिनीं फुल्लकुसुमत द्रुमदलशोभिनीं सुहासिनीं सुमधुरभाषिणीं सुखदां वरदां मातरं वन्दे मातरं वन्दे मातरं वन्दे मातरम्.
Dear ladies, gentlemen, and children, we have with us 12 IIT Madras alumni who have played pivotal technological and leadership roles in the success of Chandrayaan-3. It gives me great pride in announcing the names of these esteemed alumni of our own institute and our guests from the Indian Space Research Organization. Dr. S. Unikrishnan Nair, Director, Vikram Sarabhai Space Center.
Dr. P. Veeramuthuvel, Project Director, Chandrayaan-3.
Dr. P. Arun Kumar.
Dr. John Tarakan.
Shri Abdul Hamid.
Shri Rajiv Senan C.
Dr. Sham Rao.
Shri H. M. Raghavendra Prasad.
Dr. S. Madhavaraj.
Shri R. Karthik.
Shri B. S. Fani Dinakar.
Shri Shaktivel M.
I also request our Director, Professor V. Kamakoti, Professor Mahesh Panchagnulla, Dean, Alumni and Corporate Relations, Professor Chandra Mauli, HOD of Department of Mechanical Engineering, Professor Shankar Krishna Pillai, Department of Mechanical Engineering, to please join us on the stage. Dear sirs, we are indeed grateful that you could join us despite your hectic schedule. Thank you.
I invite Professor Mahesh Panchagnulla, Dean, Alumni and Corporate Relations, to deliver the welcome address.
Namaskaram and good morning to everybody here. Respected Dr. Unikrishnan Nair, Director of the Vikram Sarabhai Space Center, Dr. Veeramuthuvel, Program Director Chandrayaan-3, and all of my other ISRO colleagues who have played a pivotal role in the success of this great mission that has put India on the global science and technology map. Congratulations to all of you, and I want to start by by saying how proud we are of your hard work and dedication, sacrifices that has made us all proud. IIT Madras is proud to have hundreds of alumni within ISRO, almost 55,000 alumni globally who are present in over 80 countries of the world, excelling in their own fields. But this group of the 12 that are here with us today have made us all proud by doing something that no other country in the world has done. In spite of multiple attempts, as you may all have seen, the Russians attempted a similar soft landing only weeks before Chandrayaan landed. It's not because nobody tried. Everyone tried, but we succeeded. We succeeded not just in the mission, but at a cost that is unbelievable for the rest of the world. The cost that we incur to have these missions go out and do their science is a model for the rest of the world. I want to talk especially to all our students and the young school children who are here with us today. This should be a clear reminder that there is no limit to your dreams. Wherever you go to study, whoever you may become, there is no limit to what you can do with your own intelligence, with your own hard work, and with your own dedication. Friends, I want to close by talking about the broader IIT Madras ecosystem that makes these kinds of successes, that enables these kinds of successes. Being the nation's top education institution, it is our privilege to call several thousands of these amazing individuals our alumni. And this ecosystem imbibes a train of thinking to question, to do good science, and not just stop at the point of doing good science, but translate that science into something useful. That is within the DNA of IIT Madras. And through several alumni organizations, such as PALS, we try to spread that spirit to dozens of other engineering colleges around IIT Madras, to sort of bring this same stature, to bring this same train of thinking to help them as well. It's my privilege to welcome all of you today to this one-of-the-kind event, Over the Moon, and look forward to the day here. Thank you very much.
Thank you, Professor. Ladies and gentlemen, Professor V. Kamakoti, Director, IIT Madras, will now address the gathering.
Good morning. Let us start with a very big round of standing ovation to these great heroes, please. Thank you. COVID has taught us indigenous technology is extremely important to make our country a superpower in the next 25 years as we march towards the 100th year of independence. very shortly after COVID. Here is a great achievement where many interdisciplinary activities, many interdisciplinary products, components have gone in, and always we say sky is the limit, and here are the heroes who say sky is no more the limit, we can go much above it. And that is the great achievement here. There is always a question. My friend, currently director of IIT Hyderabad, used to tell, when I enter the BTech class, people are sad because they say I have not got computer science. He is a professor of metallurgy. I also told, when I enter my class, again students are unhappy, they did not get BTech IIT Bombay computer science. Right? Now the days are gone. Please understand that every field of engineering has something great to contribute. This is a very clear message to all our young BTechs and all the aspiring school students who want to do engineering. This is a very clear example that every engineering has something that we can do that could create a maximum impact. The Chandrayaan stands as an outstanding example of our times. Take pride, love the subject that you are in, love the batch you are in. And you can see here, you have mechanical engineers, you have aerospace engineers, you have chemical engineers, you have civil engineers, all of them put together on one mission project. And that is what will create maximum impact. Friends, another important thing that all of us must understand, we must protect our ideas and we must do something that brings a lot of pride to our nation. Down the line, this function is organized first to honor our great alumnus, but also to convey a message to all of you that India as a country has several very important missions. And we should reach a stage that every month we should have some function like this, where we will, as our alumnus, many of you should be on stage, and we would like to see some of the most important missions of our country led by all of you. Will this happen? Yes or no? Thank you. There are many things for which we are extremely satisfied and contented, but something that is the pivot of all this is to see our own alumnus contributing to such a beautiful, wonderful, exciting, exploratory, above the sky work that brings in a lot of contentment to all of us. I'm sure on that day when the Chandrayaan had a soft landing on the moon, the most happiest were these professors of mechanical aerospace who said, oh, my kid, my student was part of it. And that is what brings a lot of contentment to our teaching community. Thank you all for this great sacrifice and great mission and being a leading example. And I just conclude by saying that all of you, let us all pledge that we will contribute to some of these very, very important missions for our country, contribute to that and make yourself, your institute, your country proud. Thank you very much.
Thank you, sir. Dr. Unnikrishnan Nair is the director of the Vikram Sarabhai Space Center, the arm of ISRO that led the Chandrayaan program. I now invite Dr. S. Unnikrishnan Nair, our esteemed chief guest, who is also a PhD alumnus from the class of 2011, to deliver his chief guest address. Please put your hands together to welcome Dr. Nair.
Very good morning. Director of IIT Madras, Professor Kamagodi, and all other distinguished faculty on the stage, my fellow colleagues from ISRO, all faculty and staff of IIT Madras, and above all, my dear students of this great institute, very good morning. And at the outset, we have actually no words to express our gratitude and our happiness for inviting us on a Sunday, and then the entire hall is full in the early morning hours. So we are indebted to your love, your affection, and we feel proud that we belong to this institute, and then we could do something that is because of the energy and the enthusiasm we got by being part of this great institution. So I was a student, I was doing PhD here, so my stay in this campus was very short, for hardly one semester, but that one semester made a lot of changes in me, and my guru for PhD, Dr. Chandrayaan-3 is here now, he is heading the department. So it was a wonderful time working with him and the campus and the faculty and the support. So last 1 year, we have witnessed, in fact, India launched many missions. In fact, there were failures, and then we came out of the failures. But there were some unique missions too. So we thought of using inflatable systems, and then can we reduce the speed of an aircraft or a rocket part by inflating a system and then reducing its velocity from supersonic condition to subsonic condition, so that we can recover the stage and then reduce the cost. That was one experiment we did using a sounding rocket. It was a successful experiment, and we are now trying to scale it up so that in future we can recover the spent stages that are falling into sea and then reuse by using this technology. So another interesting mission that we did at Chitradurga range was a winged aircraft. We call it as a reusable launch vehicle. That is another concept of reusability. You go to, unlike a conventional satellite, it's a winged body like a space shuttle, go to space, do experiments, finally come back, and then in hypersonic condition and through the atmosphere using its wings and ailerons and rudder, come back and land on a runway. So this last phase of the experiment, that is dropping from 5 kilometers and landing, and that too in a totally autonomous way using its own onboard intelligence, we could do, and we landed with a very close to the center line of the runway. The difference was only 18 centimeters. That was the type of accuracy we could achieve. And this technology, maybe in another 2 years time frame, you will witness the winged aircraft is going to space and then come back and land on a runway. That will mark another era of reusable launch vehicle whereby we can reduce the cost. So we too had failures. We had a GSLV, F-10 was a failure. The reason was that pressure inside the cryo stage tankage was less by few millibar. Can you imagine a few millibar of pressure drop in the cryo stage has resulted in a cavitation of a pump. Thereby the stage could not be ignited. But then any failure, it's a temporary setback. But then we sit on it and find the data, analyze. We get a lot of information from that. We synthesize and then find out the solution, and it was implemented, and we had the successful GSLV F-10 launch few months back, taking our satellite to the destined orbit, intended orbit. Similarly, we know this is the time of small satellite launch vehicle. That is how we started making small satellite few years back. But its first mission was again a failure because of a small error in the onboard FDI system, where the higher acceleration was wrongly detected and the velocity trimming module was bypassed. So there was a drop of around 70 meters per second velocity, but that was enough for not keeping the satellite in the orbit. So every vehicle system worked, but finally the satellite could not stay in the orbit. So we came out of that failure, and we had the successful SSLV mission 2 a few months back, thereby putting our own small satellite. That is a powerful vehicle which will be utilized by all NGs and industry for launching small satellites from all over the world. We had three LVM-3 missions, and the first two were commercial missions. In fact, usually the rockets, the final stage will inject the satellite and then it gets separated, and then we passivate and it will be there in orbit. But for launching the OneWeb satellite series, they were having 36 satellites, and then if you want to launch multiple satellites, we had to do some changes in the cryo stage. And then we did it, and finally, all 36 satellites could be launched the way the customer wanted it. That is, you launch 4 numbers, then add a delta V to the stage, again reorient it and separate the next 4. Like that we could do, and we launched 72 satellites, thereby OneWeb could complete their constellation with LVM-3. And LVM-3 had 7 launches, and all the 7 launches have been successful, including the Chandrayaan-1, 2. And there is no wonder that LVM-3 is going to take our own astronauts to space in another couple of years. And the most exciting of all these missions, in fact, PSLV has launched Aditya. You know that Aditya has crossed the sphere of influence of Earth's gravity, and it is moving towards the L1 point, and by January first week, it will reach the L1 point, which is 15 lakh kilometers from Earth. But the most exciting mission and the most adventurous mission for all of us was the Chandrayaan mission. On July 14th, Chandrayaan satellite was launched by LVM-3 launch vehicle from Sriharikota. We know that Chandrayaan-2 was a failure, and with all the data and what we learned from the failure, Chandrayaan-3 was made rugged. Probably will talk more about it. But the task with us was to launch it successfully to the intended orbit. And the launch vehicle is giving around 10.3 kilometers per second to the satellite. And finally, 11.2 kilometers per second, the satellite will leave the Earth. So nearly 91% of the energy is imparted by the launch vehicle, and the launch phase is most critical because you have no control once the engines are ignited. But the LVM-3 has done extremely well, and all the systems performed nominally, and finally the satellite was injected perfectly into the orbit, and from there the great journey to the destination Moon started. Finally, on August 23, we soft landed on Moon like a feather, and then we achieved history by being the first country in the world to land on the southern pole. And the question is asked, why southern pole? Because southern pole has got reserves of water, frozen water, that was detected by Chandrayaan-1. And if at all, in future, if you are planning to have any habitation there, it will be nearer to the southern pole. Or if you want to take the water from the frozen water, you know that is H2O. If you can separate out hydrogen, oxygen and liquefy, you get liquid hydrogen, liquid oxygen, that is the cryogenic fuel, and that can be used for moving towards other planets like Mars and other places if you wish. And that is why there is a huge interest all over the world in going to Moon and other planets. So that we are now 4th in landing on Moon, and the first country in landing on the south pole of Moon. So that was a great achievement, and the energy and the courage that I got from this institution has helped me to deal with all the situations till its launch and beyond. So we have, I am sure all of you sitting here, they are all jewels and unique personalities. You will all have your own niche in future, and sometimes we will all come and listen to you in some other forum when you achieve something great for the country. And we have very exciting mission. I just want to say that this month we will be having the first big mission of Gaganyaan from Sriharikota. We are going to demonstrate the in-flight abort of crew escape system. You know, in manned mission, it is not the mission success. It is the safety of the crew. We are testing and ensuring that the escape system has got a very high reliability, because no launch vehicle could be made with a very high reliability. Launch vehicles are of all 0.96, 0.97 type of reliability. But you can always make a simplified, a simpler escape system with a solid propulsion, which will have 1 order higher reliability. That is what we are doing. And there where the escape system will be activated at transonic condition, that is Mach number 1.2, and we demonstrate how the crew will be rescued, and we are all looking forward to that mission. And there are many exciting missions in future. So I once again thank you all for your love and affection, and your applause and your standing ovation is more than any other prize in the world. Thank you once again.
Thank you, sir. Ladies, gentlemen, almost all of us have watched or read all the news and information on Chandrayaan-3. But how often does one get to hear a first-person account of history? Well, we are indeed fortunate to have with us Dr. Veera Muthuvel, the project director of the mission. So please put your hands together to welcome Dr. Veera Muthuvel, a PhD from the batch of 2016, to deliver the keynote address and share with us a short presentation.
Good morning to all of you. Director IIT Madras, Director VSSC, Dean ACR, and Dean Planning, and all the deans, professors, teaching and non-teaching faculties, and most importantly, students. Greetings to all of you. First of all, thanks for inviting me to be part of this event, and thanks our Chandrayaan-3 team also inviting. And this is a great pleasure for coming over here. I have done my PhD from mechanical engineering. My professor, I was guided by Professor Shankar Krishnapillai, sir is here. And I have done the particle damper based vibration suppression of an electronic package for spacecraft applications. So coming to Chandrayaan-3 success, it is by virtue of excellent teamwork and sheer perseverance, we have achieved this safe and soft landing technology on the lunar surface. And we were very happy to be, this becomes a celebration across the country, irrespective of age. And it is not only the achievement for the scientific community, it has become a country's achievement. This gives immense satisfaction for all of us. And we work towards this with utmost commitment. And the outcome has become most life-satisfying moment for all of us. And our tireless efforts, sleepless nights, and unwavering belief forms the key reasons for Chandrayaan-3 success. And we also, see, in this time we did not have, there is no failure. Failure was not an option for us. But as well, the success did not come easily also. And we crafted the lander in such a way that any path it takes, it should land. That was our strategy this time. And no room for compromise was left. And all our team, particularly navigation, guidance, control, propulsion system, sensors, and all the components worked in unison. And we also, whatever the result of confidence on the landing day was not just result of commitment and toil. It has stemmed from hundreds of lab tests and 3 important field tests, which I am going to cover it. That was a most challenging task for creating the lunar environment in Earth and proving that all our systems will work before the launch. That was one of the important tasks, and we successfully did. That's why the confidence has come along with the simulations. So with this, I will start my quick presentation. See, as you all know that 3 countries have successfully landed. One is US, Russia, and China. So initially US started with the Ranger, and they had a failure, and then followed by they had surveyor missions, and finally they had a crewed mission, that is Apollo. And Luna also has a series of program. Russians had a series of landers, and Chinese also had a series of orbiting as well as landing missions. They started with the Chang'e 1 and 2, it was primarily an orbiting mission, and Chang'e 3 started with the landing mission. And India also had a Chandrayaan program. Chandrayaan 1 was an orbiting mission, and then Chandrayaan 2 had a landing objective, but we did not fulfill the objective, hence Chandrayaan 3 was there. And there are so many landing spots As you can see in this picture, the Chandrayaan-3 is near to the South Pole. Even though we have not landed on the South Pole, but we were in terms of latitude, we were close to the South Pole. That is 69.9 degree latitude towards south and 32.3 degree east. And we were the farthest and unexplored terrain. Before the successful attempts of US, Russia, they also had a failure. US had 3 unsuccessful attempts before the successful landing. Russians also had 11 failures. And India also had Chandrayaan-2 one failure. And before to Chandrayaan-3, we had 3 recent failures also. One is Bearsheet from Israel, and Akuta R1 mission from Japanese, and Luna 25 just before our landing. Luna 25 also had a crash landing. In fact, Luna 25 has planned near to our landing spot. Unfortunately, they could not have a soft landing. So what it gives is the lunar landing missions are very complex in nature. So just to give a difference between the Earth and Moon for our space missions. So one important difference all of you know, the gravity itself is 1/6 of gravity in Moon compared to Earth, which is 1.62 meter per second square. And the next important difference is the temperature. The temperature is when sun is there, it is around 120 degrees centigrade. When sun is not there, it will go to as low as minus 150 degrees centigrade. And there is no atmosphere at Moon. So this gives, these 3 important parameters gives lot of challenges in order to characterize our systems, and also we should use different systems to break the acceleration. And another important thing is, one lunar day is equivalent to 14 Earth days. Unlike in Earth, we have one day is approximately 12 hours and one night is also approximately 12 hours. And Moon is away by 384,000 kilometers. It's elliptical in nature, but on an average, this is the distance between the Earth and Moon. And we designed our maneuvers to reach the Moon. Reaching the Moon itself is a very, very challenging task. Even though we have done in Chandrayaan 1 and 2, but still it has got a lot of challenges because we have to do it in a very precisely, the date and time and the system's performance, all have to be on dot to reach the Moon. And further we have a challenge, like I will be covering that why landing is more challenging. And we designed our maneuvers in such a way that where the launch vehicle injects, first the launch phase itself is very critical, as Director VSSC has pointed out. The first important thing is the injection parameters is the starting point. If you don't get that, we cannot even reach Moon. And unlike other spacecraft, we have to launch in a specific launch window because the landing is dictated by the launch window. So we cannot launch any given month. We typically have a window of twice in a year. So it falls somewhere in Jan, February and July, August, which means we have to realize the spacecraft well on time. The second important parameter is wherever the spacecraft injected by the launch vehicle, we have to take the energy to reach to Moon. So we have our own propulsion system which will take the from injected orbit to 4 lakh kilometer orbit. And also while going, we have multiple challenges, like it has to cross Van Allen belts. The electronic components has to survive under those radiation environment. So for which we have to design the electronic packages. So this becomes quite complex. We had some 5 maneuvers in the Earth and then again 5 maneuvers in the Moon. Finally, the propulsion module job is to separate the lander, and lander will have on its own to have a soft landing. So having covered this reaching Moon, the most important parameter is braking phase. See, we built autonomous landing sequencer. We call it as that 19 minutes of real terror. So there is no ground intervention is involved. What this time we did is what can fail, what can fail and how to handle that failure. That was our more thinking in the beginning of the project, and we built multiple mission parts. So if, for example, one sensor is not working, how do we have a soft landing? If one engine is not working, if some systems are not working, what is our strategy? And it has to decide real time. As I told, there is no ground intervention involved. So only like you, we were also watching during landing day. It's only one-way communication. We are receiving the telemetry parameters from the satellite, but we are not commanding. because we cannot even take a decision during that 19 minutes. So it is like our confidence was there just before the landing, what all tests we have done, what are the simulations we have done, how well we characterized during the 40 days journey. That gave only that was the only confidence we got. And important thing is, as I told, there is no atmosphere. So we cannot use parachute to kill the velocity. So we have to have an active propulsion system, controlled propulsion system to break the acceleration. So almost we have to break the orbiting velocity of 1.68 kilometer per second to near 0 meter per second to a targeted point. Because the targeted point is also very critical. It has got engineering constraints as well as scientific interest. So engineering constraints, when I tell, at the time of landing, the spacecraft should offer, the lug should offer the strength as well as it should offer the stability. So we do not know the terrain condition. Unlike even in Earth, you cannot get a flat terrain. You cannot land as you wish. You have to have a conducive environment for landing. So we well characterize a priori to launch using our Chandrayaan-2 orbiter high resolution camera, which is best available globally with 0.32 meter resolution. So we characterized just before the launch itself. And we decided the landing point, and that same point we need to land. So the starting point becomes very critical. Unlike in Earth, we don't have GPS in Moon. So we have to use terrain relative navigation sensor, which provides the state vectors. And during the journey, there are inertial sensor which will drift over time. So it needs to be corrected, and the propulsion system has to work. So everything has to work in unison. So that was a big challenge. And finally, the dust also, when we descend with an engine that comes with the high velocity, the dust also is a threat. So for which we designed the systems with more margins so that post-landing we don't have any surprise. Another important thing is, as I was telling, simulating the moon environment, particularly the gravity, because 1/6 of gravity in moon. So we cannot simulate the gravity. What we can do is we can reduce the mass 1/6. So accordingly, the scale down model was developed. And second important parameter is the atmosphere effect is there. How do we conduct the test with atmosphere in place? Then the third challenge is the terrain preparations, because we characterized just before the launch with all the craters and boulders based on our OHRC camera, but still we have to mimic that. So we created artificial craters and boulders at various places like Chitradurga and then Sriharikota, and we devised multiple tests to characterize these important elements, particularly navigation, guidance and control, propulsion system, sensors. So we devised 3 tests, important tests. One of the tests is to characterize only the sensors and navigation system, because the sensors, which needs to give altitude information, which needs to give velocity information, finally it should avoid the obstacle for which hazard detection and avoidance sensor, then the propulsion system characterization, and finally the lug test. The lug has to withstand the load, impact load at the time of touchdown, and also it should offer the strength and stability, for which we created a lunar soil simulant test bed. So we devised 3 important tests, and we conducted a series of tests. In fact, we had a lot of surprises in the beginning of the test, and we diligently addressed and ensured the reliability before the launch. And just having covered what has happened in Chandrayaan-2. Chandrayaan-2 also, we had a fantastic flight. It injected what we want, satellite, what is required was injected by LVM-3. We had this liftoff in 2019, July 22nd, and further earthbound maneuvers, and we brought the moon's orbit, and we also circularized that elliptical orbit. Finally, orbiter has separated the lander, and also we had a landing. So till this point of time, everything went well. The landing point, you all know, we had a crash landing. So we had 4 important phases. You can see the trajectory where it is indicated in the red curve. That is what the trajectory, expected trajectory. The dotted blue line is the observed trajectory during the day. So the first phase, the rough braking phase, where it kills maximum velocity and brings the craft to from 90 to 50 angle. And that phase went well, everything worked well. The next phase is the camera coasting phase, wherein we operate the absolute sensors to update the inertial sensor, which would have drifted over time. During this phase, we had a deviation. Almost the start of the phase itself, we got a deviation due to several factors, like we got one of the engines produced, some of the engines produced a higher thrust, and we had in the software, we had a reverse polarity. And finally, the end of the camera coasting phase, the targeted point and the observed point was well away. It was more than 24 sigma. See, even though our systems we developed for certain dispersion bands, if beyond that dispersion bounds, our system is not capable to handle. So at the start of fine braking phase, since it is very much away, it called for an aggressive maneuver. In that process, we had a tilt of nearly 360 degree. In that process, we lost the altitude and gained the velocity. At the time of touchdown, we were near to 50 meters per second, which is way beyond our lander leg capability. See, our capability was at that time 2 meters per second in vertical direction and 0.5 meters per second in horizontal direction. Whereas both the directions we got nearly 50 meters per second and no systems can survive. That's how we ended up with the crash landing. So having learned the root cause and also we pinpointed the root cause and we wanted to do a corrective action. That was our first point. The second point was maximum we had a heritage, very good heritage from the flight. Previously that 40 days went well, so utilize that heritage. The third point was, having said all those things, even though the actual problem was very minimal, but then we improvised every system in the lander. We made more robust the lander in terms of every system, like be it guidance, be it control, propulsion system, every system got improvised. And the fourth one was the simulations and the tests, which I already told. And fifth one was characterizing the systems. Even though we did in Chandrayaan-2, but we did not do it with a greater characterization in the on-orbit. So this time we devised a test in such a way that one of the example I can give is the propulsion system was characterized for the entire throttling regime. Like that we devised a test. These 5 elements has taken it for safe and soft landing. That's how the configuration was arrived in the beginning of Chandrayaan-3. I am not going into detail. There are various robustness built. One of the important thing is the multiple mission paths we built. Like for example, if nominal path is not happening, what is our contingency path? If contingency is not happening, what is the next path? Like that we built some 9 paths. Any problem is there, but still we wanted to have a soft landing. Even the landing point, we wanted to adjust the landing point. If that is not happening, last time we constrained that point, the precise landing point, but we revised even that. If sometimes on a given day, if the performance is very much deviating, but still we are freeing the downrange such that you will have a soft landing, but we cannot guarantee safe landing, but still we will have a soft landing. That was our target. Towards that, we built many paths, and also one of the important thing is, see, generally we do Monte Carlo simulations for 3 sigma, and we take normal distribution and vary the parameters and see that all the cases are going through successfully. But this time we have taken an additive extreme simulation mode. Like we had typically 176 parameters. All the parameters are unfavorable on the day. Let's say unfavorable, and we have taken into positive sense and negative sense, and we did the simulation, and we see that even that it is going through. That was our concept. Even though in that process it is over designed. You can call it as a over design, but we agree it is a over design because we cannot afford for a failure. That's the reason we took that approach. And also we built redundancies. Like some of the systems did not have a redundancy in Chandrayaan-2, so we built redundancies in every system. And this 2 other important pillars, the tests and simulations. And this I will not go through because we had a important thing, that is launch vehicle, then propulsion module, lander, rover. In addition to that, we had 3 distinct objectives. One is safe and soft landing to the designated point. Second is deploying the rover from the lander and conducting the mobility experiment of rover, because we did not have a chance last time because we did not have a soft landing. And third is deploying these scientific instruments present in both lander and rover and conduct surface experiments. This is something first time we are going. No other country has gone. And that terrain is important because we had state-of-the-art instruments in lander and rover. All these 5 instruments was operated. That is the third objective. All these 3 objectives are completely met, and it exceeded our expectations. I will tell you why it has exceeded our expectations. I have one last slide to tell. And this is something typically the trajectory and all. See, even we had, every burn we had a contingency, not only for landing, even right from launch. See, even the launch also, we have a window. If one day it is not happening, we have a contingency. Similar way for EBN 1, 2, 3, LBN also we had a contingency. And landing also, in case if you would have not landed on 23rd August, we had a backup plan of landing on 26th August, where because it is initially the orbit will come onto the west side. Right now we selected east side with the same latitude of 69.9 degree. So after several orbits, 3 days later, it comes to the west side. So we had one alternate landing site also, but keeping the south pole, near to the south pole, but it comes to west. That also was well characterized. A priori, this landing site was loaded into our onboard processor. This is some of the photograph where the lander, orbiter, propulsion module, rover on the left side, and that is how the composite module which was accommodated inside the launch vehicle. And the three important tests which I was referring, one we used a helicopter characterizing the sensors and all. We flew the scaled down model of the satellite, I would call it as another satellite, where we flew exactly from 4 kilometers till 10 meters. See, another important thing is we used last time aircraft. See, aircraft cannot hover. In our descent path, if you see, after killing the velocity, just above the landing site, we have to operate some of the cameras to avoid the obstacles, for which we have to hover. Hovering means just you have a mass into gravitational force acting downward. We have to give an upward force so that the velocity in both horizontal and velocity is not there, so that the camera is given conducive environment. So during that process, in aircraft we cannot do that type of test. So we hired an helicopter where we can do a hovering. And exactly like a flight profile we did this time, not one test, a series of tests. Almost 25 hours of flying time we used. Nearly 6 months we conducted this test at Chitradurga. And the second important test is, having characterized the sensors and navigation, we have to put propulsion system also in closed loop, for which we again created a test site, new test site, which was like a jungle. We created one test site, outdoor test. It's a unique test platform again. And we have to limit our mass to 1/6 of mass. And we hired a tower crane. And this is one of its unique test, where outdoor test. Having done all the tests, and the third test is creating a lunar soil simulant test bed, wherein we conducted a different test with the different touchstone conditions, like combination of horizontal velocity, vertical velocity, slopey terrain, flat terrain, hard surface, soft surface, on a boulder, like the different varieties of tests we have done. Just to give a quick video of it, just you will have an idea of how the spacecraft is realized at URR Satellite Center.
The Chandrayaan-3 spacecraft consists of a propulsion module and a lander module with a rover accommodated inside the lander. The propulsion module and the lander module are stacked together to form the integrated module. 6 modules were realized during Chandrayaan-3 project life cycle, out of which 3 were flight modules and 3 were special test modules, namely the integrated cold test, integrated hot test, and lander leg drop test modules.
The main function of propulsion module is to carry the lander module from launch vehicle injection till lander separation. The propulsion module was made ready for further integration with lander module.
A 6-wheeled rover is accommodated inside the lander, which would be deployed onto the lunar surface post-landing. Rover solar panel deployment and illumination test, rover standalone EMI-MC test, vibration test, thermovacuum test, and mass property measurements were carried out. All tests associated to rover were successfully completed and the rover was made ready for further integration onto lander. After integration, detailed IST, sensor level alignment and EMI-EMC tests were also carried out before shipment to ASTE Bangalore. A new facility was realized at SDSC Shar for conducting the IHT, craters and boulders simulating hazards during landing. A total of 20 tests were successfully conducted, which include 6 dry runs, 8 static tests and 6 dynamic closed-loop tests. The lander leg drop tests were carried out to evaluate the energy absorption capability, strength and stability aspects of lander legs during touchdown. A new facility was realized at iSite with a test bed with flat and 12-degree inclined drop surface. Detailed tests were carried out at damper level, single leg level, simulator level, and QM structure level for various touchdown velocities on flat and sloped surface and on lunar soil simulant and hard surface. A total of 15 drop tests at simulator level and 2 drop tests at QM structure level were conducted successfully. The objective of lander is to demonstrate safe and soft landing on lunar surface. Major elements of lander include sensors, after the completion of thermal elements in the rover compartment, the rover was assembled onto the ramp using 3 hold-downs. Detailed assembled mode IST was carried out, followed by mass property measurement, thermovacuum test, solar panel assembly and illumination test, EMI-EMC test at CATF iSite. This was followed by pre-dynamic deployment of secondary rover ramp, primary ramp and rover rollout from lander and payload deployments such as INSA and Ramba, chased, and the lander was made ready for further activities. Once the lander module was ready, it was stacked over the propulsion module to form the integrated module. EMI-EMC, vibration tests, acoustic tests were carried out. Final finishing activities such as MLI sealing, Chandrayaan-3 spacecraft was made ready for shipment to spaceport at SDSC Shar.
Can you go back to the presentation? Just presentation. Okay. First we have to. Oh, it's not coming. Thank you. Wait, it has come? Okay. See, whatever you saw, it was just up to the spacecraft realization and moving it to the spaceport. And after the spaceport, moving it to Sriharikota, we have propellant filling in both propulsion module and lander, and it was made ready and it was encapsulated. And I'm not able to see here. The next slide, can you change to the next slide? And the launch took place. The next slide. Here itself. And this is the visuals during the landing time which you would have seen. We had one camera where partially it takes the portion of lander and moon surface, and from 30 kilometer till touchdown, we were getting the visuals every 3 seconds. Even though the communication we were having every 96 milliseconds, we have higher sampling rate telemetry, but the image takes some time, so every 3 seconds we were getting this. And this also gave kind of seeing is believing more than the telemetry parameters. After the landing, another camera was operated to see that the lander is upright. Next. So this is very interesting. As I was telling, one orbiter high resolution camera which is in Chandrayaan-3 has taken a photograph of the landing site just before the landing. That picture is shown on the left side, and the right side is after the landing, the lander has been taken and captured by the Chandrayaan-2 orbiter high resolution camera. Can you click this? No, previous slide. How to go to the previous slide? Can you click this animation? So it is just an animation, and followed by the ramp gets deployed, and we also have the onboard visuals. So one of the camera was mounted in lander such a way that it captures these events, particularly the ramp deployment and rover. See, the rover is completely powered off condition from launch till landing. So first time the rover was powered on and rover is coming out of the ramp. And these are actual visuals from the lander. And this is very beautiful. See, all the time we used to refer before the launch, the lander sitting on Changi 4 or Changi 5 or our Apollo missions, Luna. So our own lander we saw from the rover. So it was away by 30 meters. The rover was taken away by 30 meters. And we captured minutely from the navigation camera present in rover, because rover is not unlike a lander. Lander has got an autonomous features in that 19 minutes, because the rover does not have that feature because it is 26 kg mass and our mass is limited. So all the functions are inbuilt with all great miniaturization. So during the operation of rover, it is always semi-autonomous, and rover cannot communicate directly with the earth. It is always communicating via lander. So we have to do a path planning, and there are so many groups involved in carrying out that activities. And whenever we move from point A to point B, we have to operate the two scientific instruments, and it goes like that for 24/7 in that one lunar day. So this, as it came away around 30 meters, we took this picture, and on the rover backside, there is one Indian flag was mounted, and the rear side of the wheel also we have our ISRO logo and national emblem. Even though that imprint we could not get on the surface of the moon because of the surface, the kind of a surface we got in that particular location. But at least the photo has been taken, whatever imprinted on the wheel. And this is, the picture also shows that our one of the chaste, it is a thermophysical experiment. The probe will get inserted into the lunar regolith about 140 mm. We have 100 mm, every 10 mm we have a temperature sensor. It will measure the temperature as well as thermal conductivity across the depth. So that also was captured by the camera on the left. You can see on the left side. And the right side is the ILSA payload. The ILSA is again a seismic activity. It will actually measure the natural seismic event as well as artificial event like rover movement and payload deployments. That also was captured. And Ramba also captured, not physically, but with the shadow we got, because Unlike the equatorial landing, the sun comes even at the top of our head also. But here, because of the south pole, the moving sun, if you see, with the maximum elevation angle of 22 degree. So even a small height will cast a long shadow. So the shadow also is moving. The sun comes from east, it goes to north, and it settles at west. So during this process, the shadow also will be a threat to the rover, as well as it is a threat to the payloads also. And as you know, that Shiv Shakti point was kept for the landing point by our Honorable Prime Minister. And from that point, the rover has traversed from the yellow point, center of the yellow point, and it took a different turn. It has to negotiate craters, boulders, because it's tiny rover, and also it has to avoid the shadows, and it has to be a scientific interest. So we operated the rover and operated the payloads. And just to give first cut scientific data, the third objective of our landing, the Chandrayaan-3, was the elemental composition of the surface, for which we had two payloads. One is alpha particle spectroscopy, where it works using extrafluorescent technique. Then second one is the LIPS, the laser based induced spectroscopy. Both are first ever built state of the art instrument, and we got an opportunity to conduct this. It measures basically the major and minor rock forming elements. So it detected even the sulfur. So we were looking for the water, but unfortunately we could not get in that particular spot. But a lot of minerals have been detected. And the second important thing is this is again a first ever lunar surface plasma environment, which is also carried out, and lot of electron density, electron temperature also was measured. And the third one is the seismic activity. It captured all the events, like artificial events, the ramp deployment, rover rollout, and the other payload deployments. And also we got one important thing is natural event also. So we are correlating what is that natural event. We know that there are a lot of meteorites can impact because of no atmosphere. That's how the craters are formed in moon. So we are just relating what kind of natural event has come. So first cut data I am just presenting. Then the thermophysical properties, as I was telling, we have first cut data across the temperature sensors, how the gradients of temperatures varies from the surface of the moon to 10 centimeter depth. So this is what I was telling, it exceeded our expectations. So one of the things is on the left side you can see we wanted to take off from where we landed with a limited elevation and with the limited downrange. So for which it was totally unplanned and our team is not prepared. But our management, our chairman ISRO and director URSC was forcing they were pushing our team to conduct this experiment, because they were telling that just one day, one lunar day is the mission, and we were on the last day. So anyway, we know that the survivability is a big question mark. So they told us we should carry forward some information for the future mission. So every program was built in that 24-hour span, and we conducted this experiment, like we call it as an op-on experiment, where we fired 2 engines in an open loop way, and we took off a small elevation and we landed. And we know it is not a flat terrain, it was sitting with an angle, and all the 4 legs are not uniform. Some of the legs are inside the regolith, and there is a terrain resistance is involved. At the time of liftoff, it should not topple. Lot of reservations were there, but for our surprise and for our fortune, it's phenomenal, this experiment, and credit goes to the management, ISRO management, trusting our team, and we came out with the flying colors. And another important thing is, you cannot lift off. There are elements which is deployed. Like as I was telling, ILSA is deployed onto the surface, chaste is inserted into the regolith, ramp is down. So all needs to be retracted and it needs to be stowed. And we did this. Generally our ISRO thing is, we thoroughly test as you fly. But we did not do this test. We were first time doing this test at moon. So we did that during the hop test, and again we deployed back. And we conducted the new location. See, lander does not have a wheel. Rover it can have a mobility and it can conduct in situ experiment. So we also got a new location, even though it is just nearby, but we got an opportunity, again deployed, and we conducted one more day of scientific instruments from the lander. That's how I told it's exceeded our expectations. So the more information is available with our ISRO Twitter, and whoever is interested, you can see this. And finally, I just wanted to tell this Chandrayaan-2 itself is a journey of the Chandrayaan-3 success itself is a lot of, it can give a lessons to the students community. So when we also came with the Chandrayaan-3 after the failure, so one thing is we all thought failing is okay, but we need to make an attempt. That is more important. And also learning from the mistake, learning from the failure is one of the important lessons we learned. And that was our first step for the Chandrayaan-3 success. That's what we believe. And after that, we have our team, entire team. So you are seeing only few of our team members here, but there are 500 to 1,000 people worked in this mission across the ISRO centers. And not only ISRO, outside ISRO also. We hired this helicopter from Indian Air Force and DRDO support and various agencies support. Even conducting this lander leg drop test, there are various vendors are involved. So it's a big team effort, and the ISRO, the main success is for the team. It's not for the few individuals who are present here. And I just wanted to thank once again for the opportunity given, and thanks a lot.
Thank you, sir.
Ladies, gentlemen, and my dear children, our distinguished guests from ISRO will now share their experience. I first invite Dr. P. Arun Kumar, Deputy Director, Earth Storable Engines and Stages. Dr. Arun Kumar is also an alumnus of our institute, belonging to the batch of 1999, holding an M.Tech degree in Mechanical Engineering.
Respected Director, Professor Kamagodi, Chief Guest and Director VSSC, Dr. Unnikrishnan Nair, distinguished faculty on the dais and off the dais, Dr. Muthuvelu and my ISRO colleagues, students and staff of this highly esteemed institution, good morning to one and all. At the outset, let me compliment the organizers for making such a wonderful, I don't know how I can describe about that kind of ambience that is prevailing here, and also for inviting me for this felicitation. I feel privileged to be here in this August gathering. As already mentioned, I did my BTech from the College of Engineering, Trivandrum, and soon after that I joined ISRO, and my assignment in ISRO was pertaining to the propulsion technology, to be more specific on the design and the development of engines and thrusters for the spacecraft programs. But 10 years later, I got an opportunity and I did my M.Tech during the 1997 and 97-99 time frame in the Mechanical Engineering department. I think at the time only they started the thermal stream. If I am right, I think the best batch of the thermal stream with specialization in combustion and propulsion. I can straight away tell from the bottom of my heart, all these subtle aspects of propulsion technology I learned from this institute. And I fondly remember the classes taken by the then director, Professor Natarajan, Professor Bhaskaran. He was the then HOD of this Mechanical Engineering department, Professor Shet, Professor Sundararajan, and other distinguished professors, and how they provide the additional information on various topics and all. I thank them. As already mentioned by Director VSSC, this institute has got a separate, vibration, which has given a lot of motivation. After going back also, I could take up some additional challenges. That way, I just want to, I'm always indebted to this particular institution, IIT Madras. I consider this as my favorite alumni. Of course, the CET is also my, I had my basic course in the CET, but then there I didn't have any primary course on this propulsion technology. So that way, this institute has given a lot of additional information, and it has reinforced my knowledge on this particular topic. As far as this Chandrayaan-3 mission is concerned, anyway, nicely, in a comprehensive way, Dr. Muthuvelu has expressed. As far as my role is concerned, what I can say is that my primary role was in the realization of 440 Newton onboard engine and 8 numbers of thrusters, what we call it as a 20-ton thrusters in the propulsion module. And in the lander module, since the lander module requires a variable thrust engine, a totally new engine, an 800 Newton throttleable engine was designed and developed so that thrust can be varied from 100% to 40%, and as well as the 50 Newton thrusters. The 8 numbers of 50 Newton thrusters also were released for this Chandrayaan-3 mission. This 800 Newton engine was extensively auto-tested for all the margins that was demonstrated. And at this point, I would like to acknowledge the study carried out by none other than Professor Sujit in the aerospace department. We had a MOU with Professor Sujit specifically to assess the combustion stability margins of this particular engine, because the engine for the first time we are varying between 100 to 40%, because earlier we have got a experience with a fixed engine. So here, what is the kind of, mainly to assess the robustness from the combustion stability point of view, and it has provided very useful information as far as this robustness aspect is concerned. Thank you, sir, Professor Sujit. It was a valuable input for us, and it has given added confidence also. And finally, on this Chandrayaan-3 mission, all the 4 800 Newton engine performed as per our expectations, turning the 19 minutes of terror into joy. Once again, I thank the organizers for giving me an opportunity. Thank you, IIT Madras.
Thank you, sir. I request Dr. T. John Tarakan, Scientist, Liquid Propulsion Systems Center, ISRO, to please come to the podium. Dr. Tarakan completed his MTech degree in Mechanical Engineering from IIT Madras in 1988.
Director, IIT Madras, Director, VSSC, Chief Guest of the Day, PD Chandrayaan-3, and distinguished professors of IIT Madras, fellow students, and dear alumni. I am grateful to the organizers for arranging such a felicitation function in my alma mater. Actually, if I look back, I joined IIT in 1986 for the MTech program in the Department of Mechanical Engineering, and I completed it in 1987. And subsequently, I joined Liquid Propulsion Systems Center, Trivandrum, and have been utilizing the experience I gained from this premier institute for the work which I have been doing. Subsequently, I joined here for the PhD program in 1998 and 1994, and completed my PhD in 2001 from the Department of Applied Mechanics in the area of injector sprays. For that PhD program, the guides from the fluid mechanics department, fluid mechanics lab were Dr. M. Balakrishnan and Dr. Ramji, and also Dr. K. Ramamurthy from LPSC. Subsequently, Professor Ramamurthy joined as visiting professor in the Department of Mechanical Engineering. And regarding the activities which I have done, or our team has done for the Chandrayaan-3, is the activities related to the experiments and the detailed simulations for the lander module. As explained by earlier speakers, we have a number of thrusters in the lander module. There are 4 800 Newton engines and 8 50 Newton thrusters. When they fire, it generates large amount of heating, and it heats the, because of the plume that is coming, the interaction of the plume with the lander module components. We will have to protect the lander modules, various modules, in order to determine what is the heat flux on the different subsystems. We have done an extensive flow and thermal simulations and determined the heat flux on various components, and that was used for the design of the lander deck and also for the propellant tanks to control their temperature within limits. And also we have done extensive analysis for the pressurization system and the different modules in the lander. As you all know, when the lander is touching the moon, it offers a flow reversal that is aiding the thrust of the engines, 800 Newton engines. We have also found out the thrust reversal, the additional thrust what we are getting from the flow reversal. That also we have worked out, and these inputs were very useful for the lander propulsion system. And we have also developed various systems, certain critical technologies for the lander propulsion system. And I take this opportunity to thank all of you in organizing and attending this particular function. Thank you all.
Thank you, Dr. Tharagan. I request Sri Abdul Hamid, scientist at the UR Rao Satellite Center, ISRO, to please come to the podium. Sri Hamid completed his MTech degree in Mechanical Engineering from IIT Madras in 2004.
Thank you. Thank you for the nice introduction. Director IIT Madras, Director VSSC, my colleagues and my faculty, my gurus, and future of the nation. Why nation? The world. Dear students, it is nice to interact with all you guys. I will not take much time, and I am not going to touch upon what all has been told about and what is going to be said about. First, I am going to address the gallery, students. So why we are exploring Moon, Mars, other planets? So the basic reason is, if you take our Mother Earth, we are, identifying it as a lithosphere, atmosphere, hydrosphere, and biosphere. So the first step is lithosphere. So Moon provides an excellent opportunity to study about the soil mechanics, the plate tectonics, and all about whatever geological phenomena that is happening. You can study as a individual parameters. Right. Our next destination is Mars. So which provides lithosphere plus atmosphere. Even though it is a depleted atmosphere, so it provides a step ahead. So you can study lithosphere in the presence of atmosphere. Next formal step is, usually people will go to Ganymede. So a planet which has water. So if we, Earth we are mentioning as 70% of covered by water like that. But if you are taking in volume, it is at fraction, 0.12% of water is available on Earth. Whereas if you take Ganymede, 20% by volume it is available. So it is like a water world. So this is our natural evolution for our study. So by studying other things, we ponder upon us and we understand merits of our own Earth ecosystem, right? So now, project director in his presentation, he stated about different phases of landing. My association with specific lander actuator performance test as well as integrated hot test. So there is a famous aerospace cliche which states about we analyze with what we know, whereas whatever is unknown to you, you should learn by testing. So that is why testing takes a central stage in any project. So in Chandrayaan mission, the project strata are organized like sensors for sensing application. Then there is an actuator, so which comprises of your wheels, momentum wheels kind of thing, and you have thrusters and engine, LAM engine, which people spoke about. So this is another strata. After that you have NGC, navigation, guidance and control software. So they are at different domains. They cannot be sitting as individual compartments. They have to be on dovetailed together to analyze the performance. So this integrated effort has happened as IHT, integrated hot test. And when we are talking about Chandrayaan-3, it is not a flash in the pan event, it is a continuum. So without talking Chandrayaan-2, we cannot come to Chandrayaan-3. So I'll take a time travel to Chandrayaan-2 and then we'll come over to Chandrayaan-3. So initially, all these hot tests were planned to be conducted using a bungee card, which used to have a bungee jumping kind of thing. No? So like that, it used to be hung in a bungee card. And when engines are firing, it offloads its self-weight, so it starts floating. So some 2-3 tests we have conducted. After that, group director, a group director of control systems came to me and he told, this is, we have characterized everything and gave, but he told for NGC to be fine-tuned, please provide a test configuration which is more realistic. That is, it should come from top and it should come down. And it is not up to landing, so that the hovering and other phases has to be simulated. That software has to be fine-tuned, tweaked. So for that, we have involved. There was a payout system design. There was a shock absorption because it will be free-falling. Once engine firing is cut, it will be free-falling. So that shock has to be absorbed, and craft should be stable. When we are talking about our programs, frugal is the bedrock. We cannot have luxury like NASA had 3 4BS landers before they are going for landing. We didn't have that luxury. So this craft should be protected. So for that sake, a tower crane, which is of 80-meter height and 60-meter gib length, has been selected. Simulated lunar surface has been created, and the hovercraft was fired. So it was in actual condition. So the moment it is firing, it will be released. There was a hold-down release system. It will be, that hovering, retargeting, landing, all these phenomena will be in closed loop with the NGC, actuator and sensor together. It will be tested. And once it is falling, the shock was absorbed very, very efficiently. And this particular configuration has helped us because in Chandrayaan-2, the sensors kind of things were minimum, whereas in Chandrayaan-3, few instruments has been added like LDV and one GPS-based sensor for, to locate it more precisely. So that with a counter mass you could manage. So that gave the flexibility also. So that is the choice which has been chosen by our review team. They gave that focus. So how to choose out of many options available. So this way tests have been conducted successfully. The software has been, fine-tuned very nicely, and the result was very obvious. So in conclusion, I just want to tell, we got certain things also. As PD in his presentation, he has mentioned the availability of sulfur. Why that is being highlighted? Because if sulfur is available, we can use it as a fuel. If at all in future, if we want to come back without carrying fuel from here, if you can source it from there itself. That is the reason why sulfur is given importance. So a book, I think, One Giant Leap, in which it is, first paragraph of the preface states that when Armstrong and Aldrin, after spacewalk, they are going back to the module. When they remove the visor, they state, moon is smelling sulfur. You can just read it. Moon is smelling sulfur. But the sample whichever they have collected, it has lost the smell, probably because of our moisture presence. So the sample whichever they have collected was named after them, aralcolite. So Armstrong, Aldrin and Colin, aralcolite. So who knows, in future, some of the new elements or new composition or new ore, whatever you are finding, may be named after you. Thank you very much for the wonderful opportunity. Thank you very much.
Thank you, Shri Hamid. I request Shri Rajiv Senansi, Division Head Liquid Propulsion Systems Center, ISRO, to please come to the podium. Shri Senan completed his MTech degree in Mechanical Engineering from IIT Madras in 2005.
Namaste. Good morning to all. Director IIT Madras, Director VSSC, PD Chandrayaan-3, all distinguished guests in the dais and off the dais. So first of all, I thank the organizers for arranging such a fabulous event on the campus. Always IIT Madras brings back fond memories, both professionally as well as personally, because actually I happened to meet my wife also here in 2003 during my second semester. So my association with Chandrayaan-3, Chandrayaan mission itself starts long back from the inception of the Chandrayaan-2 project, where the requirement of a throttling engine has come to our division. At that time it was headed by Dr. P. Arun Kumar. So our team worked for developing a throttling engine. Till that time, all our missions like Chandrayaan-1 or Mars Orbiter mission has been done with the workhorse LAM engine, which is a fixed thrust engine. So from that, a challenging task of developing a throttling engine which should work in the thrust range of 800 Newton to 360 Newton was developed without much degradation in the performance, and that has been the first ever throttling engine built in ISRO. And as the project manager for Chandrayaan-2 engines, I could coordinate with all the associated subsystems and deliver the engines in the stipulated time. So as part of Chandrayaan-3 also, as the part of the team for conducting all the special tests for the propulsion system and for all the major reviews for the clearance of the propulsion system, and is also part of the critical mission operations team at ISRO. So thanks to all your prayers of nation as well as the teamwork that powers it, so you could achieve a grand success, and I'm proud to be part of that historic event. Thank you. Jai Hind.
Thank you, Shri Senan. I request Dr. Shyam Rao, scientist at the UR Rao Satellite Center, ISRO, to please come to the podium. Dr. Shyam Rao completed his PhD degree in Mechanical Engineering from IIT Madras in 2020.
Thank you. Respected dignitaries on the dais and my dear students and faculty, distinguished faculty members. So my involvement in Chandrayaan is, you might have seen in those videos, the lander was being dropped on the surface of some white occurring soil. So we hold a patent of manufacturing highland soil which can simulate the exact properties which Apollo mission they brought back the sample. So we hold a patent, and I was part of that team, and along with Periyar University and NIT Trichy, we could invent such a process. So, and later I joined under Professor Chandramouli for my PhD. So now I would like to explain the triad, that is ISRO, IIT Madras and Chandrayaan-3. So we had already the lunar soil. The task was to design the wheel for this Chandrayaan-3 rover. So I was the one who was working on this particular wheel-soil interaction studies and estimation methods for properties evaluation while we run the wheel on the soil. And initial days, Professor Sayan Gupta of Applied Mechanics helped me in understanding certain techniques. And later I was guided by Chandramouli sir, where we told, like, we did testing, you could, if you count the number of cleats or grousers on the wheel, those are 24. So that particular study was done by our team, and during my PhD, we have proved that we did with 8 number of grousers, 16 number of grousers and 24, and 24 for the given condition and the weight of the lunar rover, Pragya rover. It was decided that 24 was giving enough traction for us. And that is how what you can see the contribution of IIT Madras in shaping my PhD as well as contribution towards Chandrayaan-3 mission. And I really thank all the faculty members, even the reviewers during my PhD. Their questions were like, when you are asked a question, then it opens up another door which you have never looked at. And the DC committee members, they did that, and it was wonderful feedback which I received during this process, and it helped in overall Chandrayaan-3 rover development. And what you could see beautifully, the rover skidding and turning to find a way for its further scientific exploration starting from lander was all possible because of the contribution of IIT Madras, ISRO, for this Chandrayaan-3 mission. And I would like to take this opportunity to thank IIT Madras for inviting and felicitating us. Actually, this particular felicitation puts us more responsibility on us to achieve higher goals and go where no one else has gone. And India holds that key. And thank you very much for shaping my thinking process and overall. Thank you. Thank you very much.
Thank you, Dr. Shamrao. Ladies, gentlemen, and dear children, we from the Office of Alumni and Corporate Relations are proud to present a short video clip in dedication to the team Chandrayaan-3. Please sit back and enjoy.
5, 4, 3, 2, 1, 0. Plus 5 seconds.
Lift off normal.
Here we have a majestic lift off of M3 Launch has also added a feather in the cap of LVM-3 rocket. You can watch the jubilant congratulatory gestures of ISRO scientists in the mission controls.
Chandrayaan-3 has started its journey towards moon.
To moon has begun now for the most awaited soft landing. We'll be closely monitoring and controlling the spacecraft from ISRO Bangalore.
जी हाँ, आप अपनी स्क्रीन पे देख सकते हैं कि हम लैंड
People are applauding. Let us all wait to hear from the Secretary Department of Space and Chairman ISRO.
எல்லைகள் இல்லை என்றே உலகுக்கே நாம் காட்டினோம்.
Ladies and gentlemen, IIT Madras would like to acknowledge and recognize the exemplary teamwork of the IITM alumni who were part of the Chandrayaan-3 mission. The extraordinary achievement of this team deserves the highest honor and recognition from their alma mater. So, without much ado, we will now begin the felicitation ceremony.
I now request Professor Chandramouli, Head of the Department of Mechanical Engineering, to introduce Dr. S. Unnikrishnan Nair, Director of Vikram Sarabhai Space Center. It will interest you to know the special connection between Professor Chandramouli and Dr. Unnikrishnan. Professor Chandramouli was the PhD supervisor of Dr. Unnikrishnan.
So the citation for Dr. Unnikrishnan, 2011 PhD from Mechanical Engineering and currently Director of Vikram Sarabhai Space Center, VSSC, India. Dr. Unnikrishnan Nair received his BTech degree in Mechanical Engineering from Mar Athanasius College of Engineering, affiliated with Kerala University, ME in Aerospace Engineering from Indian Institute of Science, Bengaluru, and PhD in Mechanical Engineering from IIT Madras, Chennai. Dr. Nair is a highly esteemed Indian aerospace engineer who currently holds the prestigious position of the Director of the Vikram Sarabhai Space Center, known as VSSC. He also serves as the Director of the Indian Institute of Space Science and Technology, IIST, Thiruvananthapuram. He is also a distinguished fellow of the Indian National Academy of Engineering, further solidifying his reputation as a leader in his field. Dr. Nair's remarkable achievements include his pivotal role in several successful space missions in India. He has gained widespread recognition for his groundbreaking contributions to launch vehicle design and his involvement in the space capsule recovery experiment, which paved the way for the Gaganyaan mission. Serving as the project director of the human spaceflight mission and subsequently becoming the first director of the Spaceflight Center, Dr. Nair played a crucial role in the entire project development. As the founding director of the Human Spaceflight Center, the youngest center in the ISRO organization, Dr. Nair has demonstrated exceptional leadership by spearheading the Gaganyaan project. Under his guidance, the Astronaut Training Center was established in Bangalore with the HSFC. He has significantly contributed to defining the crew escape system, a vital system in manned missions for crew rescue under any contingency, and was the mission director for the first crew escape system pad abort test held in July 2018. He served as the program director of the Advanced Space Transportation Program, a unified entity created for integrating the various technology development activities of human spaceflight, reusable launch vehicles, air-breathing propulsion, and advanced test vehicles. Dr. Nair's expertise and dedication were instrumental in the successful development of various crucial elements of the Gaganyaan mission, including the astronaut seat isolation project. His unwavering commitment ensured the creation of all the necessary components and subsystems for the mission's success. In his previous role as the Deputy Director of Advanced Technology, Dr. Nair made significant contributions to the Small Satellite Launch Vehicle SSLV and Reusable Launch Vehicle RLV technology demonstrator projects. Additionally, he played a crucial role in the development of the launch vehicle Mark for the Chandrayaan mission. He has received the ISRO Team Excellence Award for his contributions to SRE, the ISRO Excellence Award as Team Leader for Crew Module Atmospheric Re-entry Experiment CARE in 2014, the ISRO Individual Merit Award for the year 2014 for his contributions towards technology development for manned space mission, the ISRO Excellence Award as Team Leader for Crew Escape System Pad Abort Test in 2018, Atmanirbharta Award from Indian Society of Analytical Science in 2022, and National Systems Gold Medal from Systems Society of India in 2022. Dr. Nair's professional affiliations include membership in numerous esteemed professional bodies, He currently holds the position of National President of the Indian National Society for Aerospace and Related Mechanisms. He has authored several papers, including 12 for international journals and conferences. He holds a patent and received honorary doctorate for his contributions to human space flight activities. He is also a co-editor of a textbook on finite element analysis.
I request Professor V. Kamakoti and Professor Mahesh Panchagula to please felicitate Dr. Unnikrishnan Nair. It is the highest honor for all of us to witness this felicitation.
I next request Professor Shankar Krishna Pillai, Department of Mechanical and Engineering, to introduce Dr. Veeramuthuvel, Director of Chandrayaan-3. Incidentally, Professor Shankar Krishna Pillai and Dr. Veeramuthuvel also share a special bond. Professor Krishna Pillai was the PhD advisor for Dr. Veeramuthuvel at IIT Madras.
As the PhD guide of Dr. Veeramuthuvel, it is my great pleasure to read his citation. Dr. Palanivel Veeramuthuvel, 2016 PhD Mechanical Engineering, IIT Madras. Dr. Veeramuthuvel's journey through academia and the realm of space science has been nothing short of remarkable. With a PhD in Mechanical Engineering from the esteemed Indian Institute of Technology, Madras, and with a Masters of Engineering from National Institute of Technology, Trichy, and a Bachelor of Engineering from Madras University, Chennai, he has laid the foundation for a career that would ultimately shape the future of Indian space exploration. His doctoral thesis titled Particle Damper-Based Vibration Suppression of Electronic Packages for Spacecraft Applications was aimed at mitigating vibrations in spacecraft, a critical aspect of all space missions. His groundbreaking research was published in numerous highly reputed international journals, thus solidifying his status as a leader in the field. Dr. Veeramuthuvel's tenure at ISRO stands as a testament to his exceptional leadership and technical expertise. He served as Associate Project Director for the historic Chandrayaan-2 mission and as Project Director for the pioneering ISRO nano satellite missions, including the INS-1A, 1B, and 1C. He was also Project Manager as well as Deputy Project Director Systems for Indian Mini Satellite and YouthSat. With collaboration from CNES, the French space agency, he was involved in the Megatropic and SARA projects. In the Mars Orbiter mission, he demonstrated his ability to lead complex endeavors, resulting in resounding success. He worked closely with teams from NASA, CNES, and ESA during the realization of the above missions. His capacity to foster global cooperation while advancing India's space capabilities was truly remarkable. As Project Director of Chandrayaan-3 at the U.R. Rao Satellite Center of ISRO, Dr. Veeramuthuvel led the historic mission that achieved the safe and soft landing of Chandrayaan-3's lander on the lunar surface near the South Pole. This achievement made India the fourth country to softly land on the moon and the first to land near the South Pole. The rover descended from the lander
and conducted in situ scientific experiments from both the lander and the rover, meeting all predefined mission objectives. The rover moved approximately 100 meters to the South Pole region, collecting valuable data of the lunar terrain and conditions. Dr. Veeramuthuvel's contribution to the Indian space programs spanned 2 decades. Prior to this, he had also worked as design engineer at HAL's Rotary Wing Research and Design Center in their helicopter division. He also worked as a senior engineer at Lakshmi Machine Works. Throughout his career, Dr. Veeramuthuvel had garnered well-deserved recognition. He received ISRO Team Excellence Awards for IMS-1, Megatropics, and MOM missions. His most recent honor, the Vigyan Pratibha Samman 2023 award, bestowed by the Madhya Pradesh Council of Science and Technology and Vigyan Bharati Bhopal, is a recognition of his valuable contributions to Indian science. Dr. Veeramuthuvel's commitment to global collaboration is evident in his participation in Space Studies program conducted by the International Space University in Canada in 2014. He also completed the International Project Management course at NASA's Kennedy Space Center in Florida, USA in February 2023. Dr. Veeramuthuvel's prolific publication record in highly reputable international journals and conferences is a solid proof of his scientific contributions. In recognition of his achievements, contributions, and commitment to advancing the frontiers of space science, the Indian Institute of Technology Madras and its alumni are proud to confer the Distinguished Alumni Award to Dr. Palanivel Veeramuthuvel.
I request Professor V. Kamakoti and Professor Mahesh Panchagnula to please felicitate Dr. Veeramuthuvel.
We are overjoyed that Dr. Veeramuthuvel is now being conferred the highest recognition of the Institute for its alumni. Overjoyed that Dr. Veeramuthuvel is now being conferred with the highest recognition of the Institute for its alumni, the Distinguished Alumnus Award for the year 2024.
I request Professor V. Kamakoti and Professor Mahesh Panchagnula to please felicitate the other dignitaries. Dr. P. Arun Kumar, Deputy Director, Earth Storable Engines and Stages, ISRO.
Dr. John Farrakhan, Scientist, Liquid Propulsion Systems Center, ISRO.
Shri H. Abdul Hamid, Scientist, UR Rao Satellite Center, ISRO.
Rajiv Senan C, the Division Head, Liquid Propulsion Systems Center, ISRO.
Dr. Shyam Rao, Scientist UR Rao Satellite Center, ISRO.
Shri H.M. Raghavendra Prasad, Scientist, UR Rao Satellite Center, ISRO.
Dr. S. Madhavraj, Scientist, UR Rao Satellite Center, ISRO.
Shri R. Karthik, Scientist, Liquid Propulsion System Center, ISRO.
Shri Fani Dinakar, Scientist, UR Rao Satellite Center, ISRO.
Scientist, UR Rao Satellite Center, ISRO. I request all the dignitaries on stage to please come forward for a group photograph.
Dear ladies and gentlemen, as we near the end of the program, I request Mr. Kaviraj Nair, CEO, Office of Institutional Advancement, to propose the vote of thanks.
What an event, what an inspirational event. I think all of us got tears of joy and goosebumps several times during this occasion. Actually, many of us watched the Chandrayaan launch from the terrace of ICSR building, and it is such a pleasure to be here today. First and foremost, I would like to extend my heartfelt gratitude to our esteemed chief guest, Mr. Unnikrishnan Nair, who is the director of VSSC, and Mr. Veera Muthuvel, who is the project director of Chandrayaan mission. Sirs, your dedication to the cause of space science in India is truly inspiring, and your accomplishments are awe-inspiring. Thank you so much to all the other members of the ISRO team, Dr. P. Arun Kumar, Dr. John Tarakan, Shri Abdul Hamid, Shri Rajiv Senan, Dr. Shamrao, Shri H.M. Raghavendra Prasad, Dr. S. Madhavraj, Shri R. Karthik, Shri B.S. Fani Dinakar, Shri Shaktivel, and all. Thank you so much. Your presence has certainly made a difference and has been such a motivational instance for all the students here. My heartfelt thanks to the Director of IIT Madras, Professor Kamakoti, for your leadership of the Institute as always. To Professor Mahesh Panjaknula, Dean, Alumni and Corporate Relationships, for his tireless efforts to forge lasting relationship between the Institute and the alumni. And to Professor Chandramouli, HOD, Mechanical Engineering Department, who was also the guide for Dr. Unnikrishan Nair, and Professor Shankar Krishna Pillai, Department of Mechanical Engineering, who was guide for Dr. Veeramuthu Vel, and Professor Sarathi for his end-to-end support of this event. To all the other deans and senior faculty members who are present here, to all of our students who came with a lot of energy and created this electrifying ambience with a lot of positive energy. It's been such a tremendous experience for all here. I would also like to express our sincere gratitude to all those who worked behind the scenes to make this event a very successful one, to my colleagues in the ACR office, Padma, Shweta, Aishwarya, Jennifer, Sunita, Priya, Sudha, all of them for making this event a grand success. Our admin team, DLOs for their support coordination, Mr. Kannan's team for live streaming, campus teaser, videography and audio, communication and media team for the media support, campus display, etc. Thank you so much. It has been such a wonderful occasion. What better way one could have asked for to spend a Sunday morning. Thank you so much. Thank you everyone and have a great time. Yeah.
Thank you, sir. I request you all to please rise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उज्जल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाता जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
I request the family members and friends of our guests from ISRO to please join us on the dais for a photograph. I request the deans, HODs and faculty from IIT Madras to please stay back for a photograph. I request the family members and friends of our guests from ISRO to please join us on the stage for a photograph. They're taking a photograph. Can you stay for some time? If you can stay for some time, you can try it. I'm not assuring you you will get it. You can try it.